All right, ladies and gentlemen, welcome back to another installment of AP Chemistry Lecture Series. It's something you just can't get away from. You keep on tuning in. All right, so today what we're going to do is we're going to talk about isotopes and average atomic mass. Let's go ahead and define what isotopes are. So I'm just going to go ahead and write the term here. So isotopes, I think the definite or the literal definition is they are similar elements or the same element with the same number of protons and different number of neutrons. And so isotopes are elements with the same number of protons and different number of neutrons. So remember, the identity of an element is actually determined by protons. Right, and so I'm going to abbreviate that most times with the P with the plus symbol as a superscript. And so protons, remember, determine the identity of an element. They're found in the nucleus. The protons are the same as the atomic number on the periodic table. And so as long as an element has the same number of protons, it's the same element. All right, and then the other subatomic particle that we need to be concerned with here are electrons. My abbreviation for electrons is a small e with a negative sign as a subscript. So our electrons found in the electron cloud, electrons are actually what we can gain and lose in elements, right? Remember when we lose electrons, our elements become ions and they're positively charged. If we gain electrons, our elements again are ions, but this time they are negatively charged. And so gaining or losing electrons, not changing the identity of anything, just changing the charge of the overall atom or element. All right. Our last one that we're really concerned with here with isotopes is neutrons, and a lot of the times I'm just going to abbreviate that as a lowercase n. Neutrons really just affect the mass of the element. All right. They're found in the nucleus. A lot of the times they're added or subtracted through nuclear events. We've got this zone of stability that you might want to be familiar with. And again, that's the zone of stability. And it's a proton to neutron ratio that really runs this ratio has to be in a certain zone for the nucleus of an atom to be stable and non-radioactive. And so neutrons kind of, you could say, are causes of some elements being radioactive because of that proton to neutron ratio leaves or gets out of whack out of that zone of stability and causes that radioactivity. But what we are concerned about today is how neutrons affect the mass of the atoms. Because again, remember the definition of the isotope, we're looking at the same element, they just have different masses, and they're different masses because of the neutrons. Okay, so now let's get into how we actually discovered what these things were, and we use an instrument called the mass spectrometer. And a mass spectrometer is really, the simplicity of it is amazing, and the fact that we've used it to discover and kind of defy one of Dalton's postulates is really amazing to me. And so we're just going to sketch it out. We've got a sample, and I'm just going to label S, all right? And so from our sample, we release elements, and then we have two areas right here. The first one, we have an ionization zone, and that's exactly what it sounds like. Moving through here, we're going to remove an electron, we're going to knock an electron, and we're going to make these elements charged. I think sometimes they can either be positive or negative, depending on what kind of ionization we're doing there. But generally, ionization is going to be that removal of an electron. All right, so we're going to end up with positively charged ions here. Then, after that, we're going to reach an acceleration zone. And that's exactly what it sounds like. They're not trying to trick you or anything. This is where our elements are actually going to get sped up. We're going to move them a little bit faster. Now, this is where the really cool stuff starts to happen, is now we'll have a magnetic zone or magnetic field, and we'll have a negative in here and a positive there. So you can see, remember, we ionized our sample. We've got positive ions accelerating through this zone. Well, when they hit this magnetic field, what you'll see happen is the magnetic field is going to cause them to move. They're going to curve around. And this is where it gets really, really, really cool, is you can have multiple pathways here. Because what happens, we all understand the law of inertia. We've watched football games. We've seen large people hit small people, right, in football. And so these heavier elements, it's harder. It requires more force to move them in that magnetic field so they don't get turned as much, right? And so what we'll see here is at the end of the magnetic field is we have a detector. And what the detector does is it's just going to count how many times it's getting hit in each spot. Now, our heavy elements generally are going to, remember, because they don't get moved as much in the magnetic field, are going to hit more to the right of my drawing. But they're going to hit on that side of the detector, and then my lighter elements are going to be able to be moved more. They're going to turn more in that magnetic field, so they'll hit in different spots. But the general idea, so you kind of get a mass spectrometer, we're starting to manipulate the differences in masses that's inherent in the isotopes. We're using it to identify which ones are there. Okay, so what does a readout look for this? A lot of the times our readouts we're going to get is just going to be a histogram. And so in this particular case, we're going to call this first guy A. We'll call the second guy over here B. And so I've got A and B. We're going to say that this mass is 35, and we're going to say that this mass is 37. And yes, we calibrate that detector so that we know what that mass to charge ratio is, and we can extrapolate the mass of the isotopes. All right, and then over here, this is what's known as relative abundance. And you've seen relative abundance before back in pre-AP when we were calculating average atomic masses. And so what we see here is this is just a histogram. The more hits it gets, the higher the bar goes. And then these are just percentages. We're going to say 25, 50, 75, and then we'll say that this is 100 up top. And so what we can see based on the histogram that I've drawn here is that we end up and we can look and say, oh, for this particular element, our B isotope is 75% of the sample. And our A isotope is 25% of the sample. And it has to do, if you're looking at that, it has to do with the size of the peaks. Remember, the size of the peaks is just like in calculus, you've got underneath the curve is relative, the area under the curve is intensity. It's how many times it's happened, or abundance there. Okay? All right, and so what we're going to do is we are going to use this relative abundance over here. This relative abundance, we're going to use this to calculate an average atomic mass. All right? And so what I'm going to do is I'm going to erase some stuff down here at the bottom, and I'm going to continue on with my average atomic mass. You can probably just draw an arrow on down there. And so we're going to use relative abundance. So I'm just going to say use to calculate average atomic mass. And I abbreviated it there. I'd like you to write it out. So average atomic mass, if you think back to your pre-AP days, remember this is a weighted average, which is a term that, man, I hope everybody kind of gets. It's a weighted average, and what that means is that the more abundant a particular isotope is, the more it weighs on that average. All right? And so if we're looking at our two isotopes here, A and B, right? You look at A and B, then we understand that B, that's more abundant, it's going to weigh on the average more, so my average should be closer to 37. All right? And so this is the abundance, because we're going to use these spectrometer readouts here. We're going to use these spectrometer readouts. We'll use those to guesstimate average atomic masses. These are very popular multiple choice questions on that AP exam. And you just have to understand, what does the line actually mean? Well, the relative abundance. So if I'm looking at this, I'm not going to expect the mass to be at 36. I'm going to expect the mass to be somewhere between 36 and 37. Right? Because if it was a 50-50 ratio there, I would get each A and B weighing on the average the same, and they would average out to 36. But they're not. B is way more abundant, and so the average mass will be closer to B. And this is really what we're getting to here with isotopes, is being able to read these histograms and predict where approximately the average atomic mass is going to be. All right. Now, there is another way to do this when we've got some data and we know what the average atomic mass is, and we'll go over that in class, and so remind me to tell you about that. But for the gist of this exercise in this lecture, I need you just to understand generally how a mass spectrometer functions, why the isotopes actually are separated there, right? And then what the readout looks like and how we're going to use the readouts. Okay? All right, so hopefully I know that was pretty quick. If you got some questions, make sure you get them down on your notes. Make sure you come to class, ask those, be ready for those, and I will see you in class.